Welcome to today's paper reading. Today's paper is titled, Evolutionary Optimization of Model Merging Recipes. This paper was published on the AR14 preprint by Takuya Akiba and colleagues from Sakana AI in Tokyo, Japan. This paper introduces a novel application of evolutionary algorithms to automate the creation of powerful foundation models. The authors propose an evolutionary approach that automates the merging of diverse open-source models, effectively harnessing their collective intelligence without the need for extensive additional training data or compute resources. This approach operates in both parameter space and data flow space, enabling optimization beyond just the weights of individual models. Notably, it facilitates cross-domain merging, such as generating a Japanese language model with enhanced math reasoning capabilities. The resulting Japanese math LLM achieves state-of-the-art performance on various benchmarks, outperforming models with significantly more parameters. Additionally, a culturally aware Japanese visual language model, VLM, generated through this approach demonstrated superior performance in describing Japanese culture-specific content compared to previous VLMs. This work not only contributes new state-of-the-art models to the open-source community but also introduces a new paradigm for automated model composition, suggesting alternative, efficient approaches to foundation model development. Model merging in large language models offers significant advantages, including the need for no additional training, making it a cost-effective method for developing new models. This approach has gained prominence as it now dominates the Open LLM leaderboard, demonstrating its potential to democratize foundation model development. However, the process is often seen as a black art, relying heavily on the model maker's intuition and domain knowledge, which limits its scalability. To address these challenges, we propose the use of evolutionary algorithms to automate and optimize the model merging process. Our approach navigates both the parameter space and the data flow space, introducing a framework that integrates these dimensions. This methodology leads to the creation of EvoLLM-JP and EvoVLM-JP, two state-of-the-art Japanese foundation models, which we are excited to open source to the community. Model merging is a technique that combines multiple pre-trained models to create a single, versatile model capable of handling various tasks. This approach contrasts with traditional transfer learning, where a pre-trained model is fine-tuned for a specific task. One common method of model merging is weight averaging, which has shown significant improvements in image processing and image classification models. This technique is also effective for image generation models like Stable Diffusion. In the realm of language models, new methods such as task arithmetic and ties merging have been proposed to address the challenges of merging models, focusing on resolving parameter interference and improving performance. The DARE method further enhances these efforts by zeroing out small differences and amplifying significant ones. These advancements have been facilitated by open-source toolkits like MergeKit, which have democratized the process of model merging. The method presented in this paper focuses on creating a unified framework for automatically generating a merged model from a selection of foundation models. Central to this approach is the application of evolutionary algorithms, which are used to refine the intricacies involved in model merging. The merging process is dissected into two distinct, orthogonal configuration spaces, the parameter space, PS, and the data flow space, DFS. In the parameter space, the goal is to integrate the weights of multiple foundational models into a unified entity with the same neural network architecture, yet outperforming the individual models. This is achieved by leveraging task vectors analysis and enhancing ties merging with DARE for more granular, layer-wise merging. In the data flow space, the focus is on optimizing the inference path that tokens follow as they traverse through the neural network, preserving the original weights of each layer intact. The method limits itself to serial connections and non-adaptive configurations, reducing the search space with an indicator array. Both approaches can be combined to further boost the performance of a merged model. Figure 1 provides a comprehensive overview of our evolutionary model merge approach. It highlights three main components: the evolution of weights for mixing parameters at each layer in the parameter space, PS, the evolution of layer permutations in the data flow space, DFS, and an integrated strategy that combines both methods for merging in both PS and DFS. The figure illustrates that merging in the PS involves not just copying and stitching layer parameters, but also mixing weights, akin to blending colors. This approach is designed to operate on Japanese text, although the questions in the figure are translated to English for reader convenience. In this section, we present the experiments conducted to demonstrate the effectiveness of our evolutionary model merge approach. The primary motivation is to merge models from vastly different domains, such as Japanese language and mathematics, or Japanese language and vision. This is challenging for human experts to achieve manually. We applied this approach to evolve a Japanese LLM capable of math reasoning and a Japanese VLM proficient in handling culturally specific content. For the Japanese math LLM, we use source models including Shisa Gamma 7BV1, Wizard Math 7BV1.1, and Able 7B002, and datasets like MGSM and GSM8K. The optimization process involved CMAS, ties merging, and DARE. For the Japanese VLM, we merged Shisa Gamma 7BV1 with LLVA 1.6 Mistral 7B, using datasets such as JAVGVQA500 and JVLM Bench in the wild. The evaluation metrics included RougeL and fast text for language detection. Table 1 presents a comprehensive comparison of the performance of various LLMs. The table categorizes models into source models, 1 to 3, optimized merge models, 4 to 6, and reference models, 7 to 11. The MGSMJ column evaluates the mathematical proficiency of the models in Japanese, while the JPLMH column assesses their general Japanese language capabilities. Notably, the optimized merge models, 4 to 6, demonstrate significant improvements in performance, highlighting the effectiveness of the merging strategies employed. Detailed breakdowns of the JPLMH scores are provided in Table 2, offering further insights into the model's capabilities. Figure 2 provides a visual overview of the performance of various models on the MGSMJ task. Each of the 250 test problems is represented along the x-axis by its problem ID, and correct answers are marked with colored markers at the corresponding positions. The merged models, particularly those using merging strategies like PS and DFS, demonstrate significant improvements in tackling problems that the source models struggled with. This figure effectively illustrates the enhanced capabilities of the integrated models in both Japanese language understanding and mathematical problem solving. Table 2 presents the detailed breakdown of scores from the Japanese Language Model Evaluation Harness, JPLMH, benchmark suite. This suite consists of 9 distinct tasks, each designed to assess various aspects of Japanese language proficiency. The average score across these tasks, denoted as the average column, serves as a comprehensive indicator of overall language proficiency. For a more comprehensive view of the results, readers are directed to Table 4, which contains the full set of evaluation scores. Figure 3 presents the evolved parameter configurations following the PS merging process. Despite the uniform weighting across the 3 source models, the significant density observed in the Japanese large language model, LLM, highlights its crucial role in the merged model. This density suggests that the Japanese LLM's extensive fine-tuning from the Mistral base model contributes significantly to the task solution, aligning with the findings from our CMAS optimization and evolutionary search. Figure 4 illustrates the evolution of the inference path during the DFS merging of models A and B on the MGSMJ task. The y-axis represents the layer index, and the x-axis corresponds to the path index. Blue markers indicate the use of layers from Model A, while red markers denote those from Model B. The size of the markers reflects the magnitude of the scaling factor width. The evolutionary search process initially includes most layers from Model A and then alternates between layers from both models, showcasing the dynamic layer selection strategy in the 10B model, PS plus DFS. Table 3 presents a performance comparison of vision language models, VLMs. The table highlights the RougeL scores for 2 datasets, JAVGVQA500, which measures general VQA abilities in Japanese, and JVLM Bench in the wild, which evaluates the model's ability to handle complex VQA tasks within Japanese cultural contexts. The models compared are LLVA 1.6 Mistral 7B, the source VLM, and Japanese stable VLM, and open-source Japanese VLM. The results indicate the enhanced performance of the evolved VLM in both general and culturally specific VQA tasks. The authors propose a method using evolutionary techniques to automate the discovery of optimal model combinations from a diverse set of open-source models. This approach has successfully created new foundation models with user-specified capabilities, demonstrating the ability to merge models from different domains in novel ways. Initial tests have shown state-of-the-art results on benchmarks, including a Japanese language model capable of math reasoning and a culturally specific vision language model. Looking ahead, the authors suggest exploring the evolution of source models and the production of diverse model swarms, aiming to unlock new AI advancements through emergent generalization. The evolutionary model merging approach effectively integrates diverse expertise from the source models, but also inherits their limitations. One significant issue encountered is the lack of logical coherence in the merged models' responses. Additionally, this study does not include instruction fine-tuning or alignment, which could lead to factually flawed outputs. The integration process, while effective, faces challenges in maintaining the quality of responses due to the inherited flaws from the source models. The scope of this study excludes fine-tuning and alignment processes, which are crucial for ensuring the accuracy and reliability of model outputs. In this research, Takuya Akiba initiated the project, designed it, and started the parameter space experiments. Makoto Shing expanded the scope to include vision language and diffusion models. Yujin Tang focused on data flow merging, drawing from neuroarchitecture search and morphology evolution. Chi-Sun contributed to the implementation of the parameter space framework and model evaluation. David Ha provided overall guidance, offering technical insights, feedback, and writing assistance.